what is the magnetic field due to a long conducting wire? Okay, let's see. Let's say this is your long conducting wire. Okay, and we have to find magnetic field at this point. Let this point be P. This is not straight, okay, but let it be like this. Let's say this is the line that crosses this point, and the angle from the extreme ends is, let's say this angle is theta 1, this angle is theta 2. Okay, and let this alpha and this angle be beta. Okay, that is alpha plus beta is 90 degrees. We have to find magnetic field due to a current that is in this wire. The current flowing in this wire is I. Let's say this current is I in this direction. Now when you have this direction, you know the current will be, magnetic field will be, the direction of magnetic field is, see, right hand thumb rule, the direction of current is this, and magnetic field will be this, wrapped like this. So this is into the wall, so magnetic field intensity will be this, the direction is this. Let us consider a small element here, which the length is dl, which is, let's say, L distant from this point, origin point. Okay, this is dl and this is this distance. Now let's see, we have to find magnetic field intensity due to this dl element. So the angle between dl and I is this. Clear? Your dl is this and direction is this. So I dl cross, what you do? According to the Biot-Savart law, dB is given by mu 0 by 4 pi I dl cross r by r cube. Okay, or it is given as I dl sine theta, or let's say phi, that is the angle between dl and r. So this angle is phi. If I'm writing dl sine phi, so it means this. What is this angle? Let's say this angle is theta, that is your dl element is subtended at an angle theta on this point P. If this is theta, this will be 90 minus theta, and this will be 180 minus 90 minus theta, that is 90 plus phi. So what you get is mu 0 by 4 pi I dl, this is sine 90 plus phi. So sine 90 plus phi is, sine phi. This is sine 90 plus theta. So what you get is cos theta. So it is I dl cos theta by r square. Okay. So the magnetic field due to this small current element at P is this, magnitude is this, and direction you know is this by right hand thumb rule. Now let's see what is r. R is this length from the distance between the current element and the point. So this is r. What you get from here? R will have to resolve these L. Let's say, what is the distance from here to here? Let this distance be r. So this is fixed. L and r will vary because the moment you go from here to here, L varies and r also varies according to this. R is constant, capital R is constant. So let's write all these values dl and r in terms of capital R. See, what is that? This is for hypotenuse, this is base. So cos theta is base, that is r by small r. From here what you get, r is r sec theta. Okay, this is your first value. Now we have to find for L. L by capital R. L by capital R. This is, see, perpendicular by base. So that this is tan theta. So what you get is L is r tan theta. What we have to find? dl. So dl will be r, you know, differentiation of this, sec square theta d theta. Okay, so let's put the value here. See, dl cos theta. So what I'll write is, in place of dl, I'll write r sec square theta d theta, and then we have cos theta. And in place of r, r square sec square theta. R square sec square theta. Okay, so sec square theta cancels. Let's see what we get. So we get mu 0 by 4 pi r. I'm writing I also here. Mu 0 I by 4 pi r, and cos theta d theta. So this small magnetic field dB due to this current element is this much at this point. Direction you know. So we have to find the magnetic field due to this complete wire. Whatever be the length of the wire, we have angles to understand what is the length of the wire. So what we'll do, we will take integration mu 0 I by 4 pi r. I am taking it out, and here what you will get, cos theta d theta. D theta will be from, see, minus theta 2 to theta 1. Okay, minus theta 2 to plus theta 1. Clear? This is the point. So minus theta 2, this to this. This is 0 line. Okay, so let's rub it. So B is mu 0 I by 4 pi r. Okay, then you have cos theta d theta is simply sine theta, and this is minus theta 2 to theta 1. So this will be sine theta 1 minus sine minus theta 2. So if you remove this minus, this will be this. So what we get is mu 0 I by 4 pi r sine theta 1 plus sine theta 2. This is the value of magnetic field at this point, and the direction is this, you know, right hand thumb rule. In terms of beta, this will be, theta is 90 minus beta, so this is also equal to 4 pi r. This you can write as cos alpha plus cos beta also, because 90 minus alpha will be cos alpha. Okay, so this is the magnetic field intensity due to this wire, which is not infinite, it has a finite length at point P, which is R, capital R, distant from the wire. Okay, so this is clear. What if this is an infinite wire? I am writing it here. Okay. I am rubbing this. Okay, so if for an infinite length wire, if this is infinity, what will happen? This will increase up to pi by 2, so that theta 1 and theta 2 becomes pi by 2. This is also infinity, so like this. So pi by 2 is 1, pi by 2 is 1. Magnetic field will be, for infinite, it will be, see, sine pi by 2 1, sine pi by 2 1, that is 2, 2 2 cancels. So what you get is mu 0 I 2 pi r. Okay, direction you know, you can find it by right hand thumb rule. This is, we have computed magnetic field intensity at a point near an infinite or near a conductor by using Biot-Savart law. You saw the difficulty. The difficulty is you have to integrate it. You have to take summations of each current element. If you remember, in electrostatics we had Gauss's law, which according to which the total charge enclosed in a symmetric shape, let's say circle, and you have Q1, Q2, Q3, whatever. So the flux is equal to Q by epsilon 0. So if we have a symmetrical shape, our effort becomes very easy to when we want to find the electric field intensity. So similar to that, you saw for a simple wire we have to do so many computations. In magnetism or magnetism due to moving charges, we have Ampere's law. It is very similar to Gauss's law. Not same, it is different, but very similar to Gauss's law. What is Ampere's law? Ampere's law states that B dl dot product, this is a closed path, that is magnetic field into the length of the element in a closed path, is given as mu 0 into I. This is permeability, these are vectors, dot product. This is Ampere law, that if we have a closed surface and several currents are passing through that closed surface, if we have a surface which is called Amperian surface, if we have a symmetrical shape of that, then we can find out the magnetic field intensity by this. B dot dl closed surface is mu 0 I, where I is the total current enclosed in the surface. Now let's see this example only. We had to do so much labor to find out the magnetic field. Let's do it by Ampere's law. What we'll do, we have this wire. Okay, let's say this is infinite. I'm rubbing these signs so that this becomes easy. Okay, we have an infinite length wire. That is, if you talk of a point, let's say this point, the distance of this point, if it is r, let this distance be very less than the actual length of this wire. So we can say this is an infinite wire, infinite length wire. How to find magnetic field intensity at this point due to this infinite length wire by Ampere's law? It's very simple. What we'll do, we'll say that, see, we'll enclose it in a cylindrical Amperian surface. Okay, now let's talk of this point. This is symmetry, symmetrical shape. BDL. What will be BDL? The direction you know by right hand thumb rule. BDL enclosed surface will be, if you take B to be constant, so B will be out. You have this of DL, this Amperian surface, this, which, and inside which we have this wire. This is equal to mu 0, and let's say the current is I. What is DL? If this is one element, if you integrate it from here to here, this enclosed surface, here to here, what you will get? You will get the circumference of this circular part, that is B into 2 pi r. This is DL. So this is mu 0 I. From here what you get? Here you get that B is equal to mu 0 I by 2 pi r. This is what we get from Ampere's law. In just 1 minute we get the value of magnetic field intensity, which was very difficult from scratch, doing from scratch using Biot-Savart law. So this is Ampere's law. Another beauty is that if we have, let's say, 3-4 wires, first current is I1, second current is I2, third current is, let's say, in this direction, I3. Using this Ampere's law, it is very easy for us to find the magnetic field at a point due to 3 wires. If we use Biot-Savart's law, we'll have to take current elements of each at this point, then add them all. Using Ampere's law, it is so easy. B, and you know it is 2 pi r, this surface inside which we have this. This is mu 0. Then we are taking this direction of current to be positive. Then we have magnetic field like this. This is the direction of magnetic field. So this is positive, this is positive, this will be negative, because for this the magnetic field will be out of this wall. So this will be I1 plus I2 plus, sorry, no, minus I3, minus I3. So you know the magnetic field intensity is mu 0 I1 plus I2 minus I3 by 2 pi r. So simple. This is its beauty. Okay. Now one more thing. Let me rub this. Let's say this is our conductor. This is a very microscopic view. This is your conductor. Let's say from its center, this is capital R. Okay, this is your conductor up to infinity. We have to find what is the magnetic field intensity at this point. Let's say the direction of current is this. So you know what we'll do? We'll take an Amperian surface, a cylinder inside which this current is moving. Let's say this length is, we have used capital R, then let it be small r. The direction, you know, current is this, so this will be like this. So what will be the magnetic field? This will be B cross 2 pi r. This will be equal to mu 0 I. So you have magnetic field intensity equal to mu 0 I by 2 pi r. Okay. Now, what will be at the surface of conductor? What will be magnetic field intensity at the surface of the conductor? At the surface of the conductor, R will be equal to R, capital R, that is this radius. So magnetic field intensity will be, the strength of the magnetic field will be mu 0 I by 2 pi capital R. So this is okay. Now let's say this conductor is, it is a hollow conductor. That is, you don't have any material inside it. Now what if we take this r, small r, let me rub it. What? Our r is less than r. Then see, if we are talking of, let's say our r is this much only. Okay, so what we'll do, we'll take Amperian circle of like that. So that will be b into 2 pi r, okay, into mu 0 by I enclosed, that is your current. But this is hollow, you don't have any current because current is flowing on the surface only. So this I will be 0. So your magnetic field, the strength of magnetic field will be 0 inside a hollow wire. Clear? But if it is not hollow, let's say it is filled with material, whatever material this conductor is of, then what? Then see what happens. Our this will be b dl will be b into 2 pi r, this is clear, and then mu 0 into I enclosed. What will be the current? So current will be, let's say this is, we are seeing the cross section, so we are talking of this small r and this is capital R. Let's say it is equally distributed. Let's assume that the current is equally distributed in this whole area. So we'll have a ratio of the area, this area by this area. So if it is flowing in 2 pi r square, see 2 pi r square, the current flowing is I. So in 2 pi small r square, what will be the current? Current will be I by 2 pi r square into 2 pi r square. So this cancels. What we have here is I r square by r square. Okay. So r and this r cancels. So what we get is b by mu 0 I r 2 pi r square. Okay. So this is the strength of the magnetic field inside a solid conductor. Okay. Let's see a very small example, but it will make it will give you some concept. Let's say we have a disk. The radius of this disk is, let's say, r. Now this disk has a surface charge density of sigma. This is your surface charge density. You know what it is? That is, if the charge is q, it is q by, what is the area? Pi r square. So this is surface charge density, sigma. Now we have to find, and it is moving with an angular velocity of omega. This is your angular velocity. What will be the magnetic field intensity at the center? This is a very good question. So how we proceed? This is your disk. I think the question is clear to you. This is your disk which has a surface charge density of sigma. It is rotating at an angular speed of omega. Since charges are in motion, obviously it will create magnetic field. So what is that net magnetic field at the center? Now if you remember, magnetic field due to a circle, a loop, circular loop, is given as mu 0, the current in that loop, by 2, and if r is the radius. This, you know, we have found the magnetic field, strength of magnetic field at the center of a circular loop. So it is this. How to find for this disk? Okay, let's say we take a small element, current element. This radius is r, and a small thickness of this radius. So let it be dr. So what will be the charge on this circle in circular loop? Let's say that small charge is given as area into surface charge density. So area will be 2 pi r into dr. This is area. 2 pi r is the circumference into the thickness, that is area, into surface charge density sigma. So this is the small charge. What will be the small current due to this charge? See, omega is given as 2 pi f frequency. So frequency is omega by 2 pi. That is, the unit of frequency is per second. So if you multiply dq by frequency, what you get? You get current. Charge per unit time. This is frequency is per unit time. So charge per unit time. So what you get is 2 pi r sigma dr into frequency. What is frequency? Frequency is omega by 2 pi. So 2 pi cancel. What you get? The small current due to this circle is r sigma omega dr. Okay, so we have this charge. So let's say our dB is, what is it, r sigma omega dr. So r cancel. Now let's see. So this is dB. So what will be the net magnetic field? It will be, integration will be from 0 to r, because the variable is dr, so it will vary dr. This will vary from 0 to r. So 0 to r, this is mu 0 sigma omega by 2. Mu 0 sigma omega by 2, and this is only dr. So dr will be r minus 0. So this is simply mu 0 sigma omega r by 2. This is the magnetic field, strength of magnetic field at the center due to this charged disk. Clear? So this is a simple example, but this should build some understanding of how to calculate magnetic field. So try yourself, try some questions by yourself, and let's see.